So I'm gonna show the deformed shape, and I told you one of the most also powerful thing in ETABS is the auto mesh. So if we basically what we did last time that we asked the software to auto mesh the slab without dividing anything, and we make it general, but I told you we can, for example, unlock the model, and then before we do the analysis, we can come at the Analyze tab, and there's something it's called Auto Mesh setting for floorings. We can make it rectangle. We can make this 0.5 and then hit OK. Same thing with the slab, with the, the walls. Can make it 0.5. And then I can run the analysis. Okay, so that's for the analysis of the slab system. So we're gonna wait until it finish the analysis and see how it looks like. And I'm gonna show you how exactly the same process of replicating the story look like to SAP 2000. Just like, do you guys remember how we did replicate in SAP 2000? We select this story without the boundary condition or without the fixation in the first floor, and we hit edit, replicate, and then we listed how many stories we want to replicate. So we are gonna do the same thing here and see how it's different. All right. Okay, can you see? It becomes rectangle, looks much better. Maybe if you want, you can check the deflection in the middle here was 1 meter mesh and 0.5 meter mesh, regular and or not regular. So you can check, see how it's different it is. There will not be much difference, but you can try. Let me tell you something. What happens when we increase the mesh size? Like the mesh size was 1 meter and was irregular. Like the software picked the optimum shapes that is going to make the analysis much faster. Okay, but when we decrease the mesh size, what happened? We created more points the software is going to do averaging or going to do interpolation at or going to do analysis, finite element analysis at, right? So we increased everything. So we are expecting that it's going to take more time. You didn't notice that. Why? Because this is only one story. But if you have 60 stories or 100 stories, it's going to take a lot of time. Okay? So you will tell me, so what is the best that I can do? Should I do 1 meter, 2 meter? I want to make my analysis fast. You can do this if it's needed. Like, for example, why we decrease the mesh size here? Because we want to get better bending moment. We want to calculate the bending moment at the slab here. Like, let's say, for example, I make the mesh 0.5 by 0.5. It gives me bending moment of 2 ton meter. But when I did with a bigger mesh, it gives me 3 ton meter, like 50% more, or maybe 25% more. That means more reinforcement and more material. So I want a less mesh size just in the slab. But when I do seismic analysis or lateral load analysis, I don't need this much size. Because when I do lateral load analysis, when I build my 3D model and push with earthquake, and I'm gonna tell you when we do dynamic analysis, all what I need from the slab is the mass. I don't care how the mesh size look like. I just need the floor is well connected with the columns and the shear wall so that the lateral load resisting system can feel the masses of the slab. But don't care what is the mesh size of the slab is or how is the bending moment accurate here. So dynamic analysis or lateral load analysis is different from gravity load analysis. So sometimes we do stuff in the gravity loads that we don't need in the lateral load analysis. So I did a 2D model. That's still a 2D. It's a 1 story and it's a 2D model. And yeah, you will tell me, okay, it's a 3D. Yeah, it's a 3D, but I didn't include the total story, just 1 story alone. So I can't rely on this information. And by the way, when you run this and you run the SAP 2000 model, this one is going to get less bending moment. Why? Because it models the columns, not hinges. There's columns, okay? So the columns absorb the moment from the slab system. All right. So that's at gravity. So we do it for gravity load analysis. We want to find out what is the bending moment of the beams and the slab if it's loaded by the dead and the live load, and then we design this slab. But when we do lateral load analysis, we only design for seismic or wind. So we want to find out if this building got hit with a wind or seismic, how it's gonna deform. And I mean, who is gonna deform is that what we care about is the columns and the shear walls, the lateral system. And to model this, I model the slab as a masses. So I want to make sure that the mass is modeled properly, not the mesh is done properly, like not the mesh is that accurate, because I only care about just the mass of the slab. So we're gonna get in depth in the, not in depth, but I'm gonna tell you the summary of what we do in the dynamic analysis. So right now you understand that if I want to get the bending moment of the slab, I need the mesh to be accurate. But if I want to do lateral load analysis, maybe the mesh can be bigger so that I can model the mass, not the bending moment. Okay, I'm just like giving you some hints why we do this. All right, so right now I made sure that my models is good, so I can actually right now unlock the model. And then I can replicate for another 10 stories. So basically, but the thing is you have to create a stories verse. So I can add and modify grids. Right now, I only have one story, which is a story 1. I'm gonna add a grid for story number 2, 3, 4, 5, 6, 7, 8, 9, 10. And you can modify and show stories here. You can see all your stories. And by the way, there's a powerful thing here. Like, look at this table. It tells you what is the story height, what is the elevation of the story, and it asks you a really good question. Is the story a master story or not? What is the meaning of master story? Master story means that this story, there's other stories similar to it. Like you have a story number 1, and all the stories from 1 to 2 are similar, or from 1 to 3 are similar to story 1. So basically, I can say that story 1 is a master story. And if this is not master and this is not mastered, I can say that this story is similar to this and this story is similar to this. Look at that. So if I change these 2 stories and I said they are not mastered, they are no mastered. So this is going to be activated. It's going to ask you, this story is similar to what story? So I'm going to say it's similar to story 1, for example. So you will ask me a question. So what happened if I say it's similar? When it's a similar, let's say that you did mistake in story number 1, like, and definitely the mistake is gonna be replicated to story 2 and 3. So you want to change a beam size or a wall size. For everything that you are gonna do to story 1 is gonna happen to story 2 and 3. So you don't have to do it again. You want to decrease the cross section, and if you said that this 2 stories is similar to this one, everything is going to happen to the other story. So you don't have to go and change everything again and again. All right, but you have to activate this here. When you do any edit to any story, if you have this as a 1 story, so everything that is going to happen to this story or any modifications, this is only going to happen to the story that you are in. But if you change this to similar stories, so any edits that you are gonna do in this story is gonna change all the similar stories. And this is very, very powerful when it comes to tall buildings design, because you have 100 story or something. So you wanna make a change to 1 and it changed all the other stories that is similar to this one, okay? All right, I'm gonna hit okay. And here, okay. So I'm gonna, just to show you here, I'm gonna click. Yeah, you have here, oh yeah, there's another one, it's called all the stories. Okay, let's say here 1 story, I told you about 1 story, I told you about similar stories. There's another option, it's called similar stories. Let's say you have 5 master stories and there's 5 floors similar to each one. So we have 25 story and 5 masters, and each one has other 4 that is similar to it, okay? There is an option that you can make similar stories. So any change that you are going to do to the master is going to change the other 4. There is another option that you can use. It's called all stories. Let's say that you want to assign load that is typical for all the 25 stories. So if you activate all the stories, any change that you are gonna make to this story is gonna change all the stories in the building, even if they are not similar, okay? So that's really, really good option. I've used it a lot when I design buildings, okay? All right, so right now we only have one story, and if I wanna see this story, I'm gonna make this 3D. And this is how my story look like. Actually, I can make this view like this, and I can select all the elements that I have here, except the boundary condition. And then I can go to edit and replicate. And replicate here, I don't want to do a linear or radial or meta replicate. I want to do a story replicate. So story replicate is going to ask you, you want to replicate this story in what story? For me, I'm going to replicate story number 1 in all the stories from 2 to 10. That's the replicate that I want to do. Sometimes, and usually in tall buildings, not all the stories are the same. All the stories are the same. They sometimes actually go smaller. Sometimes the building has, I don't know, penthouse or something. So there's differences. So sometimes you want to replicate one story in just 1 or 2 stories, and then once you replicate this in 2 and 3, you start to draw story number 4. And once you're done with 4, you replicate it in 5 and 6. So, but in my case here, it's very simple. I'm gonna replicate this from story 10, and I'm gonna hit shift. And I wanna replicate this from 2 to 10. And it asks me if I wanna delete the original object. No, I don't. And then I'm gonna hit okay. All right, so now right now, it was replicated. And I have the full building modeled here. If you want to see the extruded view, you can click here, and you are going to see the building in like 3D sections. Okay, so I can run this model right now and see how's the bending moment look like, but it doesn't make sense because like what is gonna benefit me if I run this model and I saw the bending moment for this slab and this slab, they are all the same. I can see it for just one floor and that's it. We only do this 3D model and keep repeating it. We only do this 3D model just for earthquake and wind analysis. So that's, I want to see how the building is moving, how the drift look like, how the interstory drift, how whatever, like the shear on the shear walls. So we only do 3D to design the columns and the shear walls against lateral loads, okay? So I'm repeating it again. We do 2D models to design slabs and beams. We do 3D models to design columns and shear walls. All right, I want to show you a different way. How did we draw this building? Like, do you guys remember? When we made this building, we draw grids. We start making grids and then we start drawing. There's another way that we can import an AutoCAD file to ETABS and make it like this without grids and without anything. But you have to prepare the AutoCAD file for this. There's a way, it's called DXF file, and we create the mesh and we create everything. This way can work for SAP 2000 and ETABS. We do the meshing and everything is ready to be like to be an element. Like you can create your entire structure and import it to SAP 2000 and just put the loads and run the analysis. So that's a way, but it takes some time to finish it on SAP 2000. But ETABS has something that you can create the drawing that you have, not creating the model. Like you see the drawing, like not like the way that I told you, the DXF approach is that you create the elements, the beams, the columns, the slab, the meshes and everything, and you just assign materials, sections and loads and run the analysis. But what I'm saying here, I'm gonna, rather than drawing grids, I'm gonna draw everything in AutoCAD and bring it to ETABS and draw. So rather than I keep like, oh, I have 10 grids, I need to list the spacing between the grids in X and the grids in Y. We're gonna do everything like this on AutoCAD and just bring it because we already have the draw. Okay, but I want to do some modification to the AutoCAD file. First, okay, let's say that's the AutoCAD file for the project that we're working on, but I have lots of stuff here. So
I only want this project. So the first thing that I would do, I would select this and I will take it to a separate drawing because when I want to import this to ETABS, I don't want to import all these things, just this one. So to do this, you do Control-Shift-C, and then I'm gonna copy it from here and I'm gonna open new drawing and I'm gonna hit Control-V. And right now I want to put this somewhere. What is the best location to put this structure in?
The origin, right? If you put it here, any tax is gonna get here. You put it at 100 and 100, it's gonna get any tax at the same origin. I mean, like at the same coordinate. But what I wanna do, I wanna bring it at 0 and 0. So I'm gonna hit here, he's asking me about the point, the insertion point. So I'm gonna hit 0, 0. Okay, so right now the structure is at 0 and 0. All right, so actually I can import this to ETABS right now, but I'm gonna do a little bit of modification to this model. So the best way or the easiest way or the fastest way to draw your structure in ETABS by importing an AutoCAD file, you need to have the columns location, the rectangular area, as a polyline. Like it needs to be like, if you make it as a broken line, the software is not gonna see it as a column, just some broken lines. But if the lines are all connected as a rectangle, the ETABS can see it as a column. When we tell the ETABS this area or this layer of AutoCAD is a column, it's gonna see it. If it's a block, like for example, if I zoom into the column here in ETABS, in AutoCAD, you will find that there is some hatch inside. If the hatch is blocked, like you make a block, the boundary with the hatch as a block, the ETABS is not gonna see it as a column. It needs to be not blocked with the hatch, and it just isolated rectangle area. Okay. Like for example, I'm gonna make this. All right. Right now, I prepared actually the model. Like this is isolated from the hatch. Like if I said move, it's a little bit slow. Oh. Like if I click on this and I said delete. So right now the hatch is not as a one element with the rectangle area. So how about if I select this column and I make it block, like I said P. So right now, this column with the hatch is in one block. So it's very slow. I'm gonna close some softwares. Hopefully, computer is gonna be faster.
Everything has to be polyline.
Yeah, like when it comes to closed object like walls, columns, slab, all this need to be as a polyline. Polyline means like, okay, like let's say I make line and I draw a line like this and one like this and one like this in here. You'll feel, okay, that's a closed object, but it's not. It's like a broken lines. But if you said polyline or BL, so polyline, like let's say I make the same thing, random object, and I make the closed object. So if you click here, it's click as a one object. Okay, that's what we want for the columns. And in the same time, it doesn't need, it can't be a block. Okay, so I'm sure that I have all the columns that I have here. All these columns except the one that I made as a block here. Oh my goodness, I deleted. No, okay. One column I made it as a block, okay? For here, like if I imported these shear walls as is, all these are one block. Like if I delete, they are, oh, actually, there's the hatches separated. But let's make sure what layer is this. This layer is wall ETAPS. Okay, so we have the ETAPS wall is separated from the hatch. Like the hatch is on a layer, the wall's boundary on a layer, and they are all as a polyline. Okay. All right. Like for example, this one is not rectangle. Like let's see this one. This shear wall is a polyline. How did I draw it? Like I can actually delete it like this, and then I can say BL polyline. And I can go around this shear wall like this, line by line. Let's say, for example, you forgot to hit the option of polyline and you made all of them are broken line. Once you are finished with the broken line, you select all the broken lines that you draw and then hit join, and it's gonna join them and make them as a polyline. Okay, so right now I'm finished with drawing the boundaries of the core like here, but I didn't assign them to a layer. I'm gonna click on them and assign to layer wall ETAPS. So right now, all this is in one layer. Let's say that you made them as a broken line. So if you made them as a broken line, you are gonna hit J like here, J for join, and then they are gonna all be converted to like this, and J enter. Should be all joins. All right, that's for the walls and the columns. So the boundaries need to be joined and needs to be a polyline. How about the slab system? The slab system, same thing. I have one big slab. I'm gonna make rectangle. I'm gonna hit R, and then I'm gonna make angle. And then I have a rectangle area, but I make sure that the slab is gonna be on the layer slab ETAPS. So I don't have it here. I have a similar drawing here. And I make sure I already draw the slab in this blue line as a rectangle area. Like when I click on it, this one, maybe I can delete it and draw it again. Okay, so I have slab ETAPS here. The layer is activated. You all can use AutoCAD, right? Okay, so I'm gonna make rectangle. And I'm gonna start my slab from this corner and end at this corner. If you have locations that have voids, you can draw the voids like as a rectangle in the on AutoCAD, or you can delete them and just draw them on ETAPS when you get there. Just two small voids, you can do them by yourself. Okay, so for the beams, you can go to the layer, like make it on a different layer. So everything's gonna be on a layer. Columns on a layer, walls on a layer, slabs on a layer, beams on a different layer. So I'm gonna go to, and actually I named them differently, like all of them, like you will have beams and beams ETABS. Beams that has the two lines, the architectural beam or the structural beam. When we do them on ETABS, we'll only need one single line to represent the beam. So I go to beam ETABS and I draw a line. You can draw the line in the middle or at the corners, like you can do them anywhere. Like for example, I might do the beams here, or you can do them in the middle here, like I think I already have the beams drawn.
One line.
Hmm?
Or that the offset of the walls or the width of the walls doesn't.
Yeah, because as I told you, we model the beams as a frame element. So we make the line for the frame element. Yeah. All right. So I just want to make sure there is no multiple lines. I'm going to move this line. And this is the slab. Move. And okay, so there's already beams has been drawn here. Like I can see move like it's on a layer beam ETABS because I was trying this yesterday. So what I'm gonna do, because I don't want to having double beams when I go to ETABS. Just want to make sure here that this is as a join. Okay. Once I finished, I have the columns, I have the walls, I have the slabs and everything. You can save this as a DXF or save it as a DWG. The two extensions are fine. Like you can make it as a drawing or you can come here. You'll find that some extensions are DWG and some extensions are DXF. Let's say, for example, we're going to have it as a DXF and I'm going to call it slab through ETABS. And I'm gonna save it. All right, so I'm here. Okay. Let me tell you something. I can close this window and open completely new window. Like I can start from scratch. But what is gonna happen is I'm gonna bring my drawing, and when I ask the software, that I tell the software, this is the layer of columns, assign columns at this location. The software is gonna use the default material, and it's gonna create a cross section, and then put it like on your drawing, okay, automatically. All right. The thing is, sometimes I want to put my own material and I want to create the cross section that I wanted from this material that I wanted. So you can open a new model, and the first thing you define the material, define the cross sections that you have. Once you tell the software, assign cross sections at these columns, the first thing the ETABS are going to search, do you have these cross sections defined or not? Like, let's say you have in your project 100 columns. Some of them are 50 by 50, 70 by 70, 100 by 100. So you don't have to define all these cross sections. Once you set assign, it's gonna read the size of the polyline that you have, and it's gonna make a cross section with the same size. So that's the approach that I would like. So I let the software do this for me, and then I will go check material and go check everything, because that already he put the dimensions and put everything. But maybe at this point, I already have some cross sections defined here. I can set this as, and then I'm gonna delete this. I'm gonna import my model. But let me try the new model. Like, let's say I'm gonna hit save this one. And I'm gonna hit file, new model, and start blank. But there's different ways to do it. I'm gonna start metric, and I'm gonna start blank. Like, I don't want any grids. I just make sure that I have one story for now. Story height is 3, and blank. I don't need grids because I already have the AutoCAD drawing. And make sure that my units are consistent. All of them are meters. And the forces are ton force, and then hit OK. I make sure I'm on the versed story. This is the plan view story one. Okay. So I have here, I'm on a story one. So what I'm gonna do, I'm gonna hit file, and there's something in file, it's called import. And import, there's DXF, DWG file of the architecture plan. So we're gonna bring the architecture plan, just a drawing. But the approach that I told you before, like if I want to create the entire model, it's called DXF file of the floor. Like you are creating the entire slab with meshing and with everything. We use this one. But this one, I only want to see how's the architecture or the structural plan look like. So I'm gonna click on this, and it's gonna ask me where is it. I just name it slab 2 ETAPS, and I'm gonna open this file. So it's gonna ask you a few questions. What is the units of this file? I'm sure that these units are meter. Where do you want to bring this plan? Like I want to put this in a story number 1. Okay, not the base. And it's gonna ask you, do you want to move this? Like let's say that when you draw this drawing, you put it at coordinates 10 and 10. So if you want to move it, you can put the original in different places. Or it's at 0 and 0, you can move it to a different location. And I believe here there's something for the errors, like if you like the maximum distance between lines, I never use it. And I'm gonna hit OK. All right, we got an error. Okay. It's saying it's been used. Let's close this file. All right. I believe this error happens if you only use the DXF file. If you used, let's save it as a DWG as well. Slab 2 ETAPS. All right, I'm gonna close. Okay, I already closed both of them. And I'm gonna go to ETAPS and try it again. File, import, slab 2 ETAPS. This is the DXF meter story 1. Okay, same thing. I'm gonna hit OK. So right now it's open. So it didn't open it because it was open on AutoCAD. So once we close it, it was able to bring it. Right now, it's just a drawing. There's no structure element. There's nothing. So what I'm gonna do, I'm gonna assign something to the location of the columns, the walls, the beams, the slab, and everything. So let's see how we are gonna do it. Okay, look at this. Here on the left-hand side, there's something that's called model windows. If you open this model windows and open plan views and open architecture plan, it's going to show you all the layers that you have in this drawing, like AutoCAD. So what we want to do, we want to ask ETAPS, please. The layer that has columns in red, these layers, put a column section at these columns. Okay, so let's see what is going to happen. I'm going to right click on this layer. And I'm gonna ask ETAPS, add column object at these columns. Okay, so it put columns at all of them, all right? Okay, so we have the columns. By the way, you'll tell me there was a column that you make it as a block, but I used another file that I created yesterday that was finished. But if one column that is blocked with a hatch, the columns are not gonna be assigned. So you'll find all of them has columns assigned except the one that has, if in the walls, if the wall is in a block, not a polyline, it's not gonna see it. For a broken line, it's not gonna see, okay? All right, so if you wanna see extruded view to make sure that the sizes of the columns are created properly. All right. Here, look at this. This columns looks rectangle of 50 by 50, and this one looks like, sorry, this is square and this is rectangular. The same way that we had in the polyline with the same dimension. Like if you go to define cross sections, frame section. Let's see what these columns. So there's a frame section one. Let's modify it. You will find that frame section one, I believe this one is the 0.8 by 0.25, which is the rectangle one, and it has the default concrete material. Frame section two, modify. And this one is the 0.5 by 0.5, and it has the default section material, so I don't even have to do anything further. Okay, so I'm done with the columns. Let's see the walls. We have a layer, it's called wall ETABS. I'm gonna click on this layer, right click, and I'm gonna add a wall object. Okay, so walls has been created at all of them, right? We have one problem. I don't know, they draw the entire wall section. So right now we draw 3 walls, but it didn't do this way. I don't know why it didn't do that. But maybe you try it at home. It can't work with you. Okay, so if anything that didn't work well, it's very easy to adjust it. Like for example, I would come here and this wall hasn't been drawn. So what I'm gonna do, I'm gonna go to here to this option, draw walls. And I'm gonna select, I believe this is the wall section that has been used, and I'm gonna draw this wall by myself. Okay, I draw this wall, but by the way, from what I see here, this wall, this is a small one. I'm gonna delete this wall. And I'm gonna redraw it from the center of the new wall that I did it. So I'm gonna get back here to the 2D and then click on draw wall. And I'm gonna draw wall from here to the center of this wall, so they all can get connected. All right. So right now I have all the walls have been drawn. If you want to go change the material or something, you can go to define section for the slab. So I have a slab ETABS here that is rectangular area, so I can add area object. So we're gonna add a slab for the entire project. If you want to do like a void or something, you can come here, draw slab system or draw rectangular area, and in property you can check opening, and then you can start draw your opening like this. This is opening number 1. And you can start draw. Control C. I'm gonna zoom out. And I'm gonna draw an opening here. So I did the 2 openings. So right now I have the slab. For the beams, I would go to the beam ETABS here, the 4 lines or the lines that I drew, and I'm gonna add beam object. Okay, so it add beam object, but the thing is when you add beams, it assign a section, it's called none, like a dummy element. So if I click here where I draw the beam and click right click, there's a section and it's none. Okay, so what I'm gonna do, I'm gonna select all the beams on the that has a none section. I have one here. And I have one here. So if you look down, you will find that I selected already 4 frames. And I already have another beam here. We're supposed to be, okay, I have 5 now. I can assign frame section. Then I go to section property. All right, I don't have the section that I wanted, so I'm gonna make modify, add new property, rectangle. And I'm gonna hit beam 25 by 70 centimeter. Make sure that this is 0.7 depth, 0.25 width. Okay, and then I'm gonna hit OK. So this section is gonna be assigned for all the dummy element that were there. So I'm supposed to have here, if I clicked, okay, I'm supposed to have this frame section. I'm not sure why it doesn't show in the extruded view. But it's supposed to show up. But when I click here, I can see that I have the section property beam 25 by 70, which we are good. All right, so is it much easier? Okay, extruded view. Somehow the extruded view is not working. How about if we make this 3D? Make this extruded view. Yeah, right now it's working. So I have everything grown much easier. By the way, because I'm explaining it, it takes some time, but when you have it assigned, add column object, add wall object, add beam object, it's got it all done. If something is not correct, you can go ahead and change it correctly. Then you assign the load, replicate the story, and it's gonna be a piece of cake. Right? Do you have any questions? Okay. Let's see. All right, so what I'm gonna do, I'm gonna send you the project, but let's talk about the project at the end. So what I'm gonna do right now.
Doing the mesh yet. Whatever.
No, we don't have to. Everything in ETABS, we're gonna do analyze as auto mesh. Everything's gonna be auto mesh. We don't in ETABS, I rarely develop the mesh. I usually use auto mesh. Okay, so before I talk about the project, I need to make an introduction to the lateral load resisting system. So I'm gonna make a quick presentation. Like 30 minutes. Okay, so before we do the project, I said we're gonna have a project in this class, and it's gonna be a tall building project on ETABS. But before we start the project, I want to introduce the lateral load resisting system. Are you guys familiar with any lateral load resisting system that is being used for design tall buildings? We have talked about shear walls, right? We use shear walls to resist
the earthquake and winds, right? But there's other systems out there that can be used to resist lateral loads. Sometimes there's buildings are designed like the framing action between the beams and columns to resist the lateral loads. So, and there's the shear walls, there's outriggers, there's framed tube structure. So we are gonna go one by one and see how's each system working. But what we have been navigating over the last few lectures is the gravity load resisting system. So we have done, like we talked about flat slab. Do you guys remember when the columns, it just the slab resting on the columns directly? We talked about the beam, the solid slab, when the slab resting on beams and beams transfer to columns, that's called solid slab system. There's waffle slabs, ribbed slabs. All these are called gravity load resisting system. But when you have gravity is going this way, but when you have a lateral load, so that means there's other system that can resist the lateral load. So if you are pushing the building this way, it doesn't matter what is the slab system that you have. Like, it doesn't matter much. Matter a little bit, but it doesn't matter much if it's a solid slab, flat slab. Well, they are all masses. They are all loads on the structure. Okay. Okay, so what we are going to do right now is to see what is lateral load resisting systems that are out there. Okay, so first, as I told you, we're gonna go a little bit about historical background about tall buildings and then the lateral load resisting systems. What is the different systems out there? How to choose the most appropriate system for your structure. And then we are gonna conclude with the project remarks. So in the 1885, William Lippard introduced the steel columns, and he was able to make a 10-story steel building that is in the 80. And then the use of steel construction. So it started by steel, not concrete. And then the steel construction materials has been used. And then the thing is, when the tall buildings start, the thing is that you have a 60-story building and you don't have elevators. That's like never gonna happen. Like nobody's gonna go on the stairs for 60-story to live. So the limitation not only in the science of building tall buildings, but how can I get to the 60-story? So when the elevator techniques has been gotten be more advanced, more like tall buildings start to show up. So the use of steel construction materials and the development of elevator technologies make it like we move the height boundaries, like you start to go to 60 stories, 80 stories. Then in the 1930s, like there was a building in Manhattan, this building, as you can see, it's a 60-story building, was one of the tallest building at that time. In the beginning of the 20s, there was like, as you see, like in Dubai, how do we know Dubai? It's about Burj Khalifa, right? Burj Khalifa is the tallest building. Everyone starts to know about Dubai. Everyone wants to go there because there's one remark there, the tall building that we have. So it starts to be like an advertisement material, like this is how you make a propaganda for your country. So more brands like Chrysler and car brands, they wanted to have tall buildings so that they can get known much better. So more buildings has been built, like Chrysler building, 77 stories, wall tower buildings. So yeah, and then after World War II, more buildings start to come up. And as you all know, maybe you have seen some of these buildings. These are the tallest buildings in the world. There's one that is under construction since 2008 in Saudi Arabia. This building, the construction stopped for a while, but I believe the construction is back. So when it's done, it's going to be a 1 kilometer high, 1,000 meter height. Okay, so let's talk about lateral load resisting systems. So as a structure engineer, you need to choose the most efficient system. And when I say the most efficient system, what does it mean? Like how we can describe efficiency? Like when I say efficient system, that means the less cost and at the same time we don't compromise the safety and the functionality of the building, right? So how we can measure that? So usually we measure that by the weight per unit per meter square or per unit area, like how much weight of the structure you have per square area. Oh, I was able to have this by this, but if you make it less, that means less cost, less labor. So it's gonna be much less money, okay? All right, so however, at sometimes the ideal design conditions are really present. Why? The architecture like want to use this system or having this crazy idea. So you have to compromise a little bit of the cost, but you tell him if we're gonna do it that way, it's gonna cost this much. Do you want to do this? And then it's not his decision alone, so you have to get back to the owner for more cost, okay? So, yeah, and then as I told you, the efficiency of the structural system is compared by the weight per unit floor area, okay? So that's how we do it. So let's talk about the verse system that we have here. The verse system to resist the lateral loads is the rigid frames. So you'll tell me, so you want to tell me the columns with the beams can resist lateral loads? Yeah, they can. Definitely they can, but they will be more resistant to lateral load if you design the column beam connection in a way that it can resist moment. So when you push your building, this connection want to open. If you design it in a specific way, it's gonna take more moment. That means it can resist the lateral loads more. Okay, so the lateral stiffness of the rigid frame depends on the bending stiffness of the columns and the girders and the connection. So it depends on the lateral stiffness of the column, the beam, and the connection between them. So this is an example of a frame system. This is a simple frame system. You have the columns like here. All right. So you have like the columns here, and this is the slab system. When it gets a lateral load, what is going to happen if you have a lateral load like this? All the system is going to be pushed that way. But look at the slope of the building. So the slope of the building is very, very steep at the lower floors. But when it comes to the upper floors, it's going to get less steeper because the curve of the building is that way. So the slope at the support is much higher, but here it gets better. So the less the slope, the better the system. Why? Because when we design these columns, so yeah, the column in a story number 1 here and a story number 2 here, that means that there's a bending moment on this column that way. The more the deformation, the more the bending moment. But let's say this column moved from here to here as a pure translation. That means this column doesn't have any bending moment because the differential displacement between this story and this story is 0, so that means there is no bending moment. So the bending moment at the lower story is less from the upper story. So that means that this system is very, very efficient in the upper stories, but less efficient in the lower stories because the lower stories has, we call it inter-story drift. The inter-story drift between this floor and this floor. Okay, this is how we measure the performance of the floor, okay? So the more inter-story drift, the more internal forces and the more steel and construction materials, the more money, okay? So the conclusion is this system is good in the upper floors, not good in the lower floors. So sometimes we include the infill frame. So definitely if we have a building, especially in Middle East, we put like we don't use like much dry like I don't know, like a cladding or something. So you put masonry to around the building, and you include this masonry with the framing action to resist the lateral load. Like for example, if you have this connection and this wanna make that way, if you included the masonry, the brick walls that you have here, the brick walls are gonna act like a tie, tension compression. So it's not gonna allow this displacement to happen, or it's gonna restrain this displacement. So infilled frames also help in lateral load resisting system, okay? All right, so that's about the infilled frames. And this is the best system ever that you can use to resist lateral loads, shear walls. And it's usually used in most of the buildings around the world. Like even Burj Khalifa, it's all shear walls. This is the system that can decrease the displacement, that can make the building more rigid, that can absorb the lateral load. Okay, so shear walls are primarily lateral load, the primary lateral load resistance system. Even if you have frames inside your building, shear walls is taking most of the lateral loads or absorbing most of the lateral loads. So shear walls act as a vertical cantilevers because they are fixed at the base and then they are free all over the length of the building. And shear walls are a very good system and economical up to 55 stories. However, we use them up to like 90 stories or 100 stories because they are the best systems. Even it's gonna cost more, but it's the best systems. And why? Because sometimes other systems that are cost effective, they can't be used because architecture restraints. Okay. All right. When shear walls are combined with frames, the wall attract all the lateral loads and the frame is designed only for gravity. That's what happened. If you have shear walls, we designed that all the lateral loads are going to be absorbed by the shear walls and the frames, columns only take the gravity loads. All right, so this is actually a picture from the internet for the structural system of Burj Khalifa. If you see, all these are shear walls. Can you imagine how many shear walls? All the spaces have shear walls everywhere, from bottom to top. Okay, so this is how the shear walls, let's look at the deformed shape of the shear wall. It's like a cantilever. Do you guys remember the deflected shape of the cantilever? How much is the theta here? Zero, right? If you have a fixation, theta, the slope is zero, okay? Then it's bent like this. Look at this. Where is the inter-story drift is much more? Down or up? Up, right? So shear walls are a very and the best system down here. Like all the stories down, they're basically not moving. They are fixed to the ground. But when you go up, they start to move. So shear walls are the best or they are good in the lower stories, but they are not that good in the top stories. All right. So how about if you imagine if we combine frames, very, very strong frames with shear walls, they are going to take the good from each other. So the frame is good in the top and not good in the bottom. The shear wall is good in the bottom, and you combine them together, it's going to be much better. They are going to enhance each other. So that's a system that has a shear wall connected with a frame system. If you want to make this system much better, like you want to enhance it, like you wanted them, both of them, they resist the lateral loads and transfer the loads to each other, we need to enhance this connection between the shear wall and the frame system. So sometimes we make something called hunched girth, like something like this. You make a zoom in view and you make this, the cross section much bigger. So you enhance the connection between those systems. All right, so that's actually very, very interesting systems. Let's get more into more interesting systems. There's a system is called outrigger system. Have you guys heard about this system? So the outrigger system is something innovative. It's not a separate system. Actually, you have to have shear walls and you have to have another special system inside your building. So it's something that you can add to your system to enhance the lateral load resisting of your building. So I'm gonna draw it on the board. Okay, so let's say that this is your building. And you are an engineer, and then there's a lot of earthquake are gonna happen, and you design seismic, and you figured out that you are gonna use a shear wall system here. But even with a shear wall, like all this is a shear wall from the base until the top, okay? And you put columns and everything. Like there's actually the columns that take the vertical load, and this is the stories. Here, like this is story 1, story 2, 3, 4, 5, up to, I don't know, 100, okay? And the thing is, you design the building and everything, but there's a huge drift happening to the building. You have a 60-story, and the drift is like 0.5 meter or 1 meter. And you want to decrease this drift and decrease the forces. So what we do, we come at some stories, and we make something called outrigger. Like an outrigger is a deep beam with the height of the story. Like you come with this, like this is a wall, like drywall or something, but you make a concrete beam with a special reinforcement from this column to this column. Can you imagine if you have the length of your old building is 60 meter, you make a 60 meter length beam from the first column to the last column, and it has to be connected with the shear wall. And it needs to be connected with this column at the end, all the columns that it meets. And basically this system works like this. This is the
the outrigger, which is the deep beam, and this is the base, and you have a column, for example, at the end, and column at the start. So when this building get hit with an earthquake, whatever this earthquake look like, let's say this is the acceleration of the ground, so there's a base forces hitting the base to shake the building. So this building want to turn that way. There's a bending moment, like all the masses want to be thrown that way. So there's a bending moment on the shear wall. Like if you look at the stresses of the shear wall, there's a lot of tension here, there's a lot of compression here, and this is the stress down there. The thing is, this is gonna work as a tie, like it's gonna tie the building from the top, like you are having a strap and pulling the building, and this is gonna have a tension, like this is gonna pull this down, and this is gonna like resist that way, like compression. Okay, so this is gonna act as a tie and pulling the building in the other direction. So it's gonna make it like this. So it's gonna resist this bending moment. So there's an extra bending moment that happens. I'm looking at the action, not the reaction. Okay, if you wanted the reaction, if the earthquake is hitting that way, the reaction of the shear wall is gonna be that way, and reaction of the tie is gonna be that way. So the outrigger induce more resistance to bending moment and more resistant to the drift. Why? Because the tie action. So let's say this building doesn't have this outrigger on the top, like this cap on the top. The reaction in this column is going to be very, very small, all the columns. But once you put the outrigger, the columns are going to absorb more bending moment. So what we did is we reduced the bending moment on the shear wall, or the shear wall can take bending moment, but we add more resistance by making the columns take more forces from the earthquake. Like let's say that the earthquake is gonna hit with a force, I don't know, 100 ton, okay, and make a huge bending moment here. So rather than having just the shear wall resisting this bending moment, we are making all the columns that are connected here to resist the bending moment, but the columns at the start and the end, they take most of the bending moment. How? Because if you have a column here, the stresses is something like this. So, right? So if you get to the neutral point here, if you have a column here in the middle, it's gonna have 0 or something. But the way that you go away, the more that you can take more stresses. So this is how the outrigger works. So let's see how it's look like. It's something like this. This is outrigger in the X direction, and this is outrigger in the Y direction. And by the way, the outrigger, you can make them multiple of them. Like sometimes one of them is not enough. So you need to have one here and one here and one there. Okay. But they work better if there's shear wall holding them in the middle. Okay. But it's okay to put them and connect them with columns. All of them as columns. So what is like the options that you have? So let's say you have 2 shear walls here. What happened? You put an outrigger here and outrigger here, and make a build of outriggers around them. So the outrigger is the one that is inside that connect the shear wall with the columns, and the one on the perimeter we call it a build. Okay, so it's something like this. Sometimes we put it in multiple stories. Sometimes we put it 1/3 and 2/3 and in the top, and sometimes you only need 2, like a 2/3 and a 1. So there's an optimum location of the outrigger, and this is going to be part of the project. Some of the groups are going to have to try different outrigger location and see how this is going to impact the forces. So yeah, this is, and sometimes we make the outrigger if you have a steel system from trusses, like you make a truss system here that make the columns acting as a counter bending moments. So there's different ways that you can do the outriggers, and see how's the bending moment look like. This is a building and you have an outrigger here, and this is like you are holding the building with a tie the other side. Okay, so I believe that's almost everything about the outrigger. So we can add it to the shear wall. So let's go to the next system. There is a system, it's called the frame the tube system. What is the frame the tube system is? It's a little bit complicated. I'm not sure if we have time for it, but I'm gonna do my best. So the frame the tube system doesn't include shear wall. Oh, you'll tell me I can't build a 70-story or 100-story building without a shear wall? Yeah, you can. The way it works is we are actually, it's a shear wall and not a shear wall. It's something like the frame to tube system. How it works, you make a very, very close columns, like, let's say that you have a building layout 60 meter by 60 meter. And you are gonna put a very, very strong column at a very low spacing, like you have a column maybe 1 meter by 1 meter, and you come after 2 meter, you make the same column, and another one, the same column. You will see a lot of columns close to each other with very close spacing, and they are connected with a very, very strong beams in between them. Like the beams between them is very, very strong. So the whole perimeter of the building is gonna feel like a shear wall that has some holes. Like when you look at this building at the end, let's say columns here, here, here. This building, when you look at side view, gonna be something like this, just like a shear wall, the whole front of the building, and has some holes for the windows. That's it. So we call it as a perforated shear wall, like shear walls that has a bunch of holes. So somehow we are trying to make this building, the whole perimeter of the building, like not only a shear wall that is 3 meter, 60-meter shear wall, and 60-meter shear wall. So the whole building is gonna act as a shear wall. So if this building got an earthquake, like let's say it got a hit with a force like this building wanna bend that way. So all the columns here are gonna have like the stress is gonna be something like this. All this is gonna have tension, and then they are gonna go have compression, right? So all these columns is gonna act like this, and this is gonna have tension, 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 and here's almost zero, and here's gonna have compression, 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 compression. So the stresses are gonna be something like this. So basically, the columns are acting as a shear wall, but there's only one downside of the shear wall. It's not solid shear wall. So it's not perfect shear wall. So there's a phenomenon happens in the frame the tube system. Actually, it's called tube system, frame the tube system. It's called shear lag. So if this, like let's say a force hit that way, so we are saying that this is acting as a shear wall. If this is a really shear wall, the stress curve is gonna be something like this, a line, and this line is uniform until it comes here, something like this. But if this is not solid and has holes, voids like this doesn't be like that. Something is gonna happen, which is the strains are gonna be something like this, like this. So if it's a shear wall, it acts with a very, very good efficiency. But if it's a perforated shear wall or columns connected with beams, you lose all these resistance. And why this has happened? Imagine this as like this beams. Actually, what happened, this beams, like the beam that is here, is connecting all these columns together, right? So basically this beam wanna move, like when an earthquake happened, this column go, so this beam wanna move. So basically it's like you have a chain, like if you have a wire or something. Yeah, like this thing. So that's the beam, right? And it's connected by columns at separate point. So when it's wanna move or wanna make like a tension compression, it makes like a curve, something like this. It's you are pulling column by column. But if this beam is very stiff, the beam that connected this column is like the story height. Like this beam depth, let's say if it's 1 meter. Yeah, it's good. If it's 2 meter, it's much better. What if it's the story height? So that's actually a shear wall, right? So this beam are gonna like move as a one piece. But if it's not stiff enough, it's gonna have like a little bit of deflection. So that's actually what happened. So it pulled this column, so you are losing this. So for the frame to tube structure, the best is to decrease the shear lag. Like you are making the structure more economical, or what I mean by more economical is that you are making it more efficient and decrease this shear lag. How can I decrease this shear lag? Tell me some options, how to make
this as a shear leg. So to decrease the shear leg, I want to bring this system to be stiff enough, like that feels like as a full shear wall, solid shear wall, right? Do you guys know how can I do that? What things that I can add to my system that can make this less, the shear leg less? I mean, what can I do to make the frame the tube system feel as a shear wall?
Cross bracing.
What is that?
Cross bracing.
If you make bracing, but you are gonna close the windows, it's gonna go with the architecture. You can make the columns closer. So if the columns are closer, if the distance are zero, that means like you are becoming a shear wall. But if it's bigger, the frame the tube system is gonna be less efficient. So it's not gonna make the shear wall action. So, or increase the beam depth. Increasing the beam depths are gonna make it more efficient. So that's things that we're gonna try in the project. What if we increase the column dimension, not the spacing? So we can increase the column dimension, increase the column spacing, the beam dimension, so we can play with all that. The beam widths can help a little bit, but not much. Mostly the beam depths that helps with this. So that's about the frame the tube structure. So I'm gonna stop here right now, but next time I'm gonna tell you about other tool system related to the frame tube structure. But I believe this is good for now. So I'm gonna share this presentation, go through the different load resisting system. And once I'm finished them, I'm gonna introduce you to the project. So, all right, see you guys next time.
You're okay to download this point.
Maybe you wait a little bit. Yeah.
Do we have your model for it now?
Hmm?
Do we have your model for it?
No, it's gonna be the project. Yeah.